All right, thank you very much. So today I give a presentation on some project we have been doing in Cyprus on portable and cost-effective instruments. And I will start with a quick motivation. So as probably most of you know, is that we have to deal with aerosol particles pretty much everywhere because they have many different sources, like anthropogenic sources and natural sources. And there are different mechanisms of how particles would form, and they have an impact on climate and health. And in order to understand the processes or know what kind of health risks there are or impacts on climate, you need to do measurements, and the most important physical properties are the size and the concentration of the particles. And so measurements are a little bit tricky in the atmosphere or of aerosol particles in particular, because you have so many, it covers so many, such a broad size range. So you cannot just use the same instrument for measuring aerosol particles. You need many different instruments, and most of the instruments that are currently used are used in measurement stations, and they're very expensive instruments, and they're not always easy to operate and to process the data, and they're also very expensive. So this brings a limitation on the network, on the data that we get, because you cannot just put instruments everywhere. And we are trying to do some work now at the Cyprus Institute to make the instruments a little bit more versatile and mobile for more cost-effective air quality measurements. So basically, instead of having like just a few measurement stations, to have aerosol monitoring devices everywhere in the city. So you have more data and better data of, for example, health effects. So in the past years, there has been a lot of advances in this part of developing more lightweight instruments, and there's also some commercial instruments available. Many of them are optical particle sensors. As you can see, some examples in the pictures on the left of the slide. And there has been a work of evaluating further the AlphaSense OPC, because it showed promising sizing capabilities. So what these instruments are doing is they have a laser inside, and they measure the size and the concentration of the particles, and then they report something like PM 2.5 or PM 10 data. But of course, the size and the cost efficiency of these instruments comes also with increasing uncertainties of these instruments, and many of those are connected, for example, also to the sampling procedure. So they have sometimes only passive sampling, and of course they have also cheap electronics inside, and all these kind of things are making them obviously not as accurate as lab grade instruments. But the AlphaSense OPC showed some promising results in the initial tests, but the biggest issue with this instrument was that it's only comes with a fan for sampling. So you have problems with artifacts of sampling, and but it was possible to do a small modification of that by installing a small pump, sorry for that, a small pump and an orifice, so you have a controlled flow. And with this modification, this instrument has been put inside a box, which has now a user interface and also some network capabilities, and this is tested now at field stations. But of course, before you test an instrument at the field, you should characterize it first in the lab, and this has also been done by using PSL spheres. So those have known sizes, and then the instrument has been put into a chest freezer chamber where you can control the relative humidity and the temperature, and then it has been compared to a GRIM OPC, which is used in measurement stations routinely. And here in the mid graph, you can see the comparison for the sizing capabilities. Here you have to see have to note also that the GRIM OPC obviously has some issue with the sizing, so it overestimates the size quite a bit, but you can see that at least it's very consistent in the sizing capabilities. While for the modified OPC, you can see that the data is quite scattered, but okay, that's expected in a cheap sensor. If you compare the instrument now in terms of concentration measurement, you also see some deviation, and so both the deviation in the sizing and in the concentration is mostly associated to the counting. So you would have coincidence of particles, so not single particle counting anymore, but counting 2 or more particles at the same time. And this leads to this underestimation of concentration and the overestimation of size. And this can be corrected. So in this slide here at the bottom right, you can see the red data, which is the original data, and the line 1 would represent the comparison instrument. And if you do this correction, all these data points up to about 2.5 micrometer fall on the one line, and they're basically within 30%, which is rather satisfactory. So this is makes this instrument as a cheap sensor that you can put everywhere in a city quite promising. One disadvantage you always have with OPCs is that you lose all the smaller particle sizes. So this is now moving, so I'm moving now to a different project where we have been looking exactly at the smaller particle sizes. And as probably most of you know, is that when you look at smaller particle sizes in measurement stations, most commonly applied is an SMPS system, which can measure very accurately with a high resolution the size distribution of small particles by moving them in an electrical field and measuring the electrical mobility. So there's also other lightweight instrument for smaller particles existing, but in this project we looked at making an SMPS system more cost efficient and more mobile. And this is some work that has been published already in 2016, where we found that it's possible to make DMAs out of plastic. So you coat plastic and then you use it, you copy a stainless steel DMA basically, and then you can see in the curve to the right that the performance is really very, very promising. So it works basically the same. And this initiated a whole new other work of building various different DMAs. So we have built now a parallel plate DMA, which is very compact. So here we actually use metallic aluminum plates, but all the parts around it are also 3D printed. And so we're basically taking advantage of 3D printing as a fast prototyping technology and cost-efficient manufacturing method. So when you look at the performance test of this parallel plate DMA, you see that especially the sizing is quite good compared to the expected size. You also see that you get this nice size distributions. When you look here, you also see that the transmission is quite good through this instrument, but the resolution is quite a bit lower than you would have it predicted by the theory, which is probably due to some surface roughness on the aluminum plates. But given that this can be built like really very fast and very, very cheap, this is a downside which is still acceptable for us. So another issue that you have very often when using SMPS systems for measurements is that you need a certain amount of time to scan the entire voltage range to get the full size distribution. And this takes some time. And when you want to measure in scenarios where your aerosol is changing rapidly, like that would be the case in new particle formation situation, but also it's relevant if you put your instrument on a fast moving platform, such as airplanes or UAVs or also cars. you might not want to wait for the scanning time for your instrument to measure. So this is another work that we did with 3D printing. We printed DMAs which have, instead of one monodisperse outlet, have like 3 monodisperse outlets. We did 2 different versions of that, one sampling from the inner electrode and one sampling from the outer electrodes, all again 3D printed. And so this has the advantage that basically you can have 3 instruments in one. So you always measure 3 sizes. You can operate it either scanning or with a constant voltage. So you get like basically 3 sizing slots out of it, but all the time. So you count one size all the time, and you can see the variability like that. So also here, of course, we did performance tests. We did it in a tandem setup where we size selected monodisperse aerosol particles in a first DMA, and then we scanned in the multi-outlet DMA, and you see that the same sized particles show up at different voltages as expected. This is now the graph for the sampling at the inner electrode, and this is one for the sampling at the outer electrode. The results for the outer electrodes are a little bit better, and we are associating that with the fact that when you sample from the outer electrode, all the tubes that go outside can be of the same length, and you basically have the same pressure drop there, while if you sample from the inner electrode, the tube lengths are different, and you have probably more losses because you sample the smaller particles closer. Here you have a longer tube, and also that is resulting in more diffusion losses probably. So right now we are working on making a full lightweight SMPS system. So we have already all the components as prototypes available. So we did a prototype neutralizer, which is a bipolar corona neutralizer, also small, also 3D printed, and we have the parallel plate DMA. And we had, in the scope of a project, we had a Cypriot company build a prototype CPC for us also. And all of these parts are currently tested individually, but eventually we want to put that together and put it at our atmospheric observatory that we have here in Cyprus and compare it to a TSI SMPS. Currently the parallel plate DMA is there with a commercial neutralizer and a commercial CPC. So basically the plan is to multiply that, and then you can either operate it as something where you operate DMAs in parallel, so you get a faster response, or you can multiply it, so you put the SMPS in much more locations and get more data, or put it on UAVs. And so there's still a lot of work to be done in this field. So now I'm getting to the conclusions of this presentation. So I can conclude from the low-cost optical aerosol sensors that they're really very, very simple to operate, and you can put them in many locations and get data from that. You have a little bit compromise on the accuracy, and you have to deal with sampling artifacts if you are in scenarios where you cannot use, for example, a diffusion dryer, and it carries a high potential for improvement with simple modifications of these instruments. So that's something very successful at this point. And we're working now on doing a full 3D printed SMPS system, and have a much cheaper and hopefully much more compact instrument that might have comparable results in the measurements to the now existing instruments. So with this, I'm closing, and thank you for your attention.
Great, thank you so much, Anne. Really interesting work. So already a few questions have come in, so I'll take those. So Martin Irwin says, exciting developments. Did I miss the final payload weight for the SMPS?
Well, It's difficult to give a number. Like with the parallel plate and all the parts together, probably it would be aiming below 2 kilos. But yeah, we still have to put all of it together. We are now also having a lightweight flow box, and but yeah, now it gets basically to all the surrounding parts, like the high voltage power supply and so on, but still add some weight to it.
Yeah. And then he also asks, how about the power requirements? Any ideas of what the power requirements are?
Well, I don't know at this point. I mean, the CPC, the most power requirement is the Peltier element. So you still have some power consumption that you cannot really avoid. But yeah, we hope that we can put everything with the battery. But yeah, these are all the next steps right now. It's really prototypes on the still in the lab and at the station, and yeah, those are definitely the things that we have to work on next.
Great. And maybe just could you expand? I know the CPC wasn't your work, but is it kind of getting down to comparable length scales as the DMA that you've made?
The dimensions of it, like? Yeah,
that's right.
Well, it's about the length from here to here would be about 15 centimeters approximately. 15. Oh. Yeah, so with the inlet and then the optics probably about 20-23 centimeters. So the optics right now is still a TSI block. So this is something that's developed in Finland currently within the scope of the project. So yeah, but it's quite small if you don't look at all the surrounding things that need to power it at this point.
Okay, good. And then Anonymous asks, does this modification require regular maintenance during using? I don't know which modification they're referring to. Maybe Anonymous could expand on that. Let's assume the DMA.
Well,
that's what you've spoken most about.
The DMA. So since the 3D printing DMAs with the coating date back now a while, so we have some experience on long-term performance. So there you need to redo the coating every now and then, like maybe every year or so. But for the parallel plate, since the plates are aluminum, we expect there to have no issue like that. I mean, you need to just clean it like you would clean a normal DMA occasionally. So yeah, that's if that was meant with this question, and that's the answer.
Sure. Well, you answered it well. I'm not sure that was if that was their intent or not. And then a final one from Oliver Bischoff. Have you published the charging efficiency of the corona neutralizer?
No, this has not been published. There is actually a very similar corona neutralizer that's already been published. It's like Pramod's work in, I forgot the name, but there is a publication out where they also built a small bipolar corona charger, and they published it some years ago. And this is very similar, but we are currently still testing ours, and none of this work has been really published yet. Okay.
Yeah, of course, interesting to see, whether there are challenges with impurities hitting the corona needle and the like.
Yes, well, yes, there is definitely challenges with this kind of things to make the needles operating well and reproducible for a long time. So this is certainly something to consider in that. But yeah, we're still in the prototype phase, but hopefully it will come all together.
All right. Well, Anne, thanks so much once again.